Okay, so welcome everybody. Here is databases in the microservices world. Here's the part where I tell you I am definitely going to post the slides on my site tonight, and you're going to check tonight and tomorrow, next week, next month, and then in about 3 months you'll get tired of pushing refresh and you'll email me, and in about 6 months I'll reply and say, no, I'm definitely going to post them on my site tonight. I've been that guy. I've chased the speaker for 3 months, 6 months trying to get the slides, and I hate it too. Which is why you can go to robrich.org right now and click on presentations. And here at the very top is databases in the microservices world. Here are the slides. They are online right now. While you're there at robrich.org, click on About Me, and you'll get to this page that talks about some of the things that I've done recently. I'm a Microsoft MVP, a friend of Redgate. AZ GiveCamp is wonderful. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. It is a lot of fun. Or if you'd like a GiveCamp in your area, hit me up on Twitter or by email, and let's get philanthropy installed in your network as well. Some of the other things that I've done, SQL Source Control Basics, that was a lot of fun to build. Mine is Chapter 8. I worked on the Gulp team as a core contributor in version 2 and version 3. And one of the things I'm particularly proud of is I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woohoo! So there's my claim to fame, is my coveted .NET Rocks mug. And if you'd like a .NET, no, I'm just kidding. So, databases in the microservices world. Online right now. We talked about this guy. Application architecture. So we started off with spaghetti architecture. We moved to lasagna architecture, and we've transitioned now into ravioli architecture. Or said differently, we do a big ball of mud, and we kind of moved to N-tier architecture. And now we've moved from N-tier more towards microservices. I really like this spaghetti lasagna ravioli metaphor. That's really cool. But said differently, we started out with monoliths and we moved towards microservices. Monoliths here on the left were really powerful in that deployment was hard and we didn't want to do it. So we did it really infrequently and we deployed as much as we could in one go. That made sure that that pain wasn't as intense as it could be, and so we got all of the pieces together in one shot. As we got to containers, as deployment became less painful, as we got better at deploying, then that kind of freed us up to deploy lots of little pieces. So we got to microservices like this on the right. Now microservices are really great. They add a layer of indirection, but they do have some downsides as well. Now I have more complexity and more of my pieces are available. Well, as we move from monoliths to microservices, our ideal is to have a data source for each microservice so that each microservice can store its own data. And now we don't need to say, well, who owns this table? Because, well, the microservice that created it owns that table. Microservices. Each microservice does one job. It's easy to deploy, probably with containers. We can scale each microservice independently so we can use our resources much more efficiently. And each microservice is simple and therefore easy to replace. If we find that we need to upgrade a microservice or replace a microservice, we can take down that one microservice and prop up a new one, just implementing all the interfaces of all of the things that consume it. One of the core tenets of microservices, it owns its own data. And that is wonderful. When a microservice owns its own data, then, well, as we replace the microservice, we can upgrade the data store. Or as we remove a microservice, we can remove the data store. Who's using this table, this column, this field? Only this microservice. So when the microservice doesn't use it anymore, we can remove it. That's perfect. Well, we want to get to that, but usually we end up in a scenario that is very different. Usually we end up in something like this, where we have lots of microservices. We've refactored our application into lots of pieces, and yet we go back to the same old database. Why do we end up with microservices and a monolithic database? Well, probably because the DBA said no. And I get it, but I don't get it. A DBA's job is to ensure uptime. And the more that we deploy stuff, the more that we separate it, the more that we refactor, the more that we change things, the more the uptime is potentially in jeopardy. So a DBA trying to protect uptime will probably push against our goal of separating the database into pieces. Well, taking that at a little bit different angle, the goal of the DBA is to ensure data safety. And if we look at data safety, each microservice may be actually more safe because it's more isolated. It's never large enough to need to scale in interesting ways. Or if it is, only that piece needs to scale. And so we can use less on hardware. We can use less of our systems to accomplish this. That's really cool. Well, the critical pieces here, if we have lots of little databases, did we remember to secure it? Did we remember to back it up? It's really interesting when we start into these small databases, when we go, well, we'll just restore that database from, oh, oops. To get to these small databases, we probably need mechanisms of automation, or at the very least audit, to ensure that every database gets secured correctly and enrolled in backups. So if we must use a monolithic database, if we're stuck in a scenario where we can't get to smaller databases, then we can build bounded contexts. A bounded context is that portion of the database that is relevant to this portion of the business code. So let's take an example, like a shopping cart. So in a shopping type of experience, an e-commerce experience, we need to be able to show products. We need to show the product description, all pretty. We need to show all the product images. But we don't need to own all of that data. In the fulfillment center, we probably need to own different data. We need to own the order. Well, kind of the order lines. We don't really care about the fancy product description or the product pictures. We only care about how many of what product ID is there, and can we fulfill it and ship it to the correct address. We can see that there's a bounded context around the product catalog and a little bit into order entry for the shopping cart experience. And we can see a different bounded context around order lines and shipping address for the fulfillment side. These separate bounded contexts allow us to treat our database as if it was small pieces, micro databases, if you will. But yet the database underneath is still one big database. But let's get into that. How would we get to micro databases? Well, we probably need enough automation to be able to spin them up quickly. We need that automation to enroll them in backup and in authentication. But when we get to micro databases, now that's really, really cool. We've gotten to the point where each microservice can own its own data. And when we need the data of another microservice, we can call the other microservice to get at it. Well, kind of. Are there some inefficiencies here? Like, how do we do joins? How do we do common things? Let's dig in through each of those scenarios in the micro database scenario. Now, in a micro database, we assume that we have enough automation to be able to spin up these database pieces quickly and securely, enroll them in authentication, and enroll them in backup automatically. And now we've gotten to the point where we have micro databases to match our microservices. Perfect. So micro database. A micro database is owned by exactly one microservice. When that microservice gets upgraded, the database can get upgraded. When that microservice gets removed, that database can get removed. We know that only that one microservice owns this micro database. So other microservices can call this microservice to get at its data. That's perfect. But how do we do joins? What happens if we want to, harvest a report that talks about all of the orders that we've gotten? Do I need to call that microservice, passing in every next customer ID to see if I can get the order totals? Well, we can do some really interesting things with event sourcing here. We can publish events from each microservice to an enterprise service bus, perhaps Kafka. And as we publish these events to Kafka, then others can listen to those topics and take action. So how do we do joins? Well, we subscribe to the Kafka topic that is relevant to our data, and we pick off the pieces that we need. And we store it in our micro database. When it comes time to join, we have all the data that we need because we grabbed that from event sourcing. Joins are really powerful when we have event sourcing, and it allows us to subscribe to another microservice's data rather than query for another microservice's data. That's perfect. We're still doing it through a common pattern. We're not reaching into the other guy's database. Okay, so micro databases. Who owns the customer record? Now here's another scenario where we hit it where it's like, well, if we just had one monolithic database, then we could have that one gigantic customer record and everyone who needs it could just add fields to it. Well, yes and no. As we get into micro databases, we want to shrink that down. But who owns the customer record? Should the shopping cart own the customer record? They need it to be able to assign orders to it. Should billing own the customer record? Billing is going to keep sensitive data like credit card details. Should human resources? That's another area where details about a particular person are really sensitive and don't want to be shared with anyone. Well, how about sales? Sales saw the customer first. The lead or the prospect is the first time that we ever saw this. If they're entering in new customers, surely they should own the customer. Well, kind of. There's a difference between a lead or a prospect and a customer. To be able to place an order for a customer, I need to have a full shipping address. A lead, I may only have their first name and their phone number, that they texted me. Or maybe I only have the details off their business card. I don't have the full thing. So if sales owns the customer record, then by the time we go to ship an order to it, we may not have enough information. Instead, let's build a new microservice, a customer microservice, where it owns the primary key and the account number, making sure the account number is unique, and that's all. This customer microservice is responsible for incrementing the primary key and ensuring that the account number is unique. Everything else about the customer can be put in a different microservice. So the shopping cart can contain customer profile details that are specific to the shopping experience. What orders did you place recently? What items do you like to purchase frequently? Billing can create its own customer profile that links back to the customer. This can include the sensitive credit card information that isn't shared outside the billing microservice, but they do have a foreign key off to the customer service. Human resources can keep all of the sensitive data in their customer profile, which is very different than anyone else's customer profile. As human resources needs more fields for the customer, they can add those additional fields to their customer profile, which doesn't affect the shopping cart, the billing. And as sales and as sales tracks leads and customers, at the point where a lead converts into a customer, that's when sales can start to create that account number in the customer service. But all of the lead details, all of the contact details associated with that lead, all of that can live in the sales portion of in the sales microservice. That's perfect. We were able to separate these micro databases into bounded contexts applicable to each thing. And the things that are shared get put into a central spot where all of the others can call into it. If I need a new account, I can call into the customer service and request a new account number. That's perfect. So microdatabases, we were able to get to the point where we have a specific data store for each microservice because we have automation around creating databases and automation around enrolling them in backups and authentication. So there's never a time when a microservices database will go down where we can't just spin it back up or restore it to a certain point in time. That's perfect. We've achieved microdatabases. Now, the cool thing about microdatabases, when each service owns its own data, those data stores don't need to be the same type. Now, that's perfect. Each microdatabase can best accomplish the needs of that microservice. And we could have more than one database if we need to store different types of data. Each microdatabase doesn't need to be the same vendor or the same type of database. They don't all have to be the same database vendor or the same database type, said me, right now. I like this quote. Okay, so because we now have the ability to use different types of data stores for different types of applications, let's take a look at the data stores that we can choose from. Now, some of these database types will be really familiar. Some of them may be brand new. Because we're not in that monolithic database methodology, we can grab the ones that make sense if we have the automation to enroll them in backups and authentication. So we'll look at relational databases, document databases, graph databases, Keyvalue, Timeseries, search, object or blob stores, column stores, and one that may be new to you, Nosql. In each of these types, we'll take a look at the characteristics, the pros and cons of each type, best use cases, and examples. Now, I'm definitely not here to sell you a particular database, but rather to offer you options for when you need a particular database of a particular type to be able to find that thing that you need. First up, relational databases. We can think of these like a spreadsheet. Maybe we have an Excel spreadsheet, and in Excel, each row is one piece of data, and each column is identical across that thing. So maybe we have a zip code column, or an address column, or a name column. In a relational database, each row represents one thing, and each column is a single type of data, and each cell represents the data in that cell. We have consistent rows and columns. We have SQL queries. One of the big things about relational database is these SQL queries. It's English-like, where we can kind of reason through the query and take a look at what kind of data we're selecting here. These SQL queries are great in being able to identify the data, and SQL has really been tuned as a language, as a concept, for decades, making these SQL queries really efficient. One of the major benefits of relational databases is ACID compliance. Let's dig into that. ACID compliance. Atomic, consistent, isolated, durable. We know that when our query gets submitted to an ACID compliant database, it will either fully succeed or fully fail. There will be no case where part of the data is updated and part of the data is not. If it's ACID compliant, we know that the entirety of that thing will succeed or fail. If it fails, we can retry it, or we can alter our data and try again. If it succeeds, we know that that data is stored correctly. By comparison, we may have eventual consistency. We can think of eventual consistency like a credit card statement. If I go into Starbucks and I order a thing, and then I go check my credit card statement, it may or may not be there. Now, eventually, by the time they mail me my month-end statement, that Starbucks charge will definitely be on my card, and it'll be for the exact right amount. But right after I make that purchase, if I go read my statement right away, I may not get the right answer. Now that's okay, eventually it will be right, but right now we don't have that data. So eventual consistency compared with ACID compliance. ACID compliance, we know that the moment that we finish saving, we can query again and get that data back. With eventual consistency, we can't. And in a relational database, ACID compliance is one of those primary features. That's really cool. So looking at a relational database, in the pros column, we have a strong schema. We can do table joins. We have this very optimized query engine, and we have this compatible familiar syntax. And I grant that some SQL engines will have slightly different SQL queries, but for the most part, there's a select, there's a from, there's a where, there's a join. I can kind of wander my way through these and get the hang of each of the database syntaxes. On the downside, it is optimized for storage size. When we start looking at relational databases, we'll look at normal form, third normal form, perhaps. What that means is that we're splitting it out so to avoid redundancy, to shrink the size on disk. Now, disks aren't as expensive as they used to be, so reducing the amount of storage space is less of a concern right now. It's unfortunate that we optimize for that concern we no longer have. Relational databases are generally not designed to scale horizontally. A relational database is built in the time when we pretty much had one machine. And so to scale is to make that machine bigger. It was built before multiple cores, before networking was a thing. Well, that does yield some difficulty in scaling horizontally. And it does yield some difficulty because eventually, vertically, there isn't a bigger box, or there isn't more RAM, or maybe that box is way too expensive. We're also now dependent on that one box. So if that one box fails, our database is down for a time. It's best with an ORM, a tool that will allow us to resynthesize our objects back from our relational database. And another downside, because we have a strong schema, we need to migrate that schema from time to time. If the database schema changes, we'll need to tell the database about that. So here's some examples of relational databases, and relational database is a pretty good default. I bet if you're in a monolithic database environment, your database is a relational database. They're really good because of ACID compliance, because they have that fast, durable syntax, and so they make a good default for pretty much everything. Well, if you have unique constraints, then we can reach out into other database types to get more performance in a particular feature. Next up, we'll talk about NoSQL. Well, kind of everything that isn't SQL is NoSQL, but in particular, document databases. Document databases will store JSON data, where we have keys and values. The value might be a nested array or a nested object, and so we can store the entire JSON data together in one document. So rows become documents, and documents can contain whatever data they contain. The documents in a collection, or said differently, the rows in a table, don't all have to be the same. These documents in this collection can be specific to whatever the application needs at that particular point. Now on the upside, they can be anything. On the downside, they can be anything. These are generally optimized for reads, and they're optimized for reads so that we can go grab all the data that we need to accomplish a particular task. Now on the upside, document databases are a much more modern creation, and they were built with distribution in mind. So horizontally distributing document databases is usually built into the data store. By comparison with SQL databases, we often have to start hacking through replication or other mechanisms to try and get the data to be horizontally scaled. Document databases generally aren't ACID compliant. They are eventually consistent. And so once I write, I have to wait a little bit for it to reconcile before I can read that data back again. Document databases. On the upside, I have no schema. So as I change that schema, or if different rows need to have different schema, then I can just write that. On the downside, because they have no schema, my application probably has a schema. It probably believes that this object has a certain shape, And so we have a whole lot more error handling where I need to compensate for missing values in a particular data shape. On the upside, it's denormalized. So I don't need to worry about joining data and reading from other tables. On the downside, I kind of can't do joins. There is not really a concept of joins in document collections. Well, kind of. I can do a second query to the other collection to get the related data, and document data stores that support joins kind of do that. But that's not a SQL join. That is a second query that just happens to get zippered in together. Another downside is because this isn't SQL, I probably have a different SDK or a different query experience for each language. We're probably querying with JSON documents and some interesting things. So we don't get that advantage of the really optimized and tuned SQL engine. So that's document databases. They kind of give us the other side of things. We don't have a strong schema, which means we don't need to maintain it, but we do need to teach our application how to handle things better without it. We don't have the barrier of horizontal scaling, but we do end up with eventual consistency instead of ACID compliance. So here's some examples of some NoSQL databases. These are best when I'm optimizing for reads, when I need to grab the entire thing at one go. So for example, a news site or a CMS, where I want to grab the news story and the first few comments and the author's name and information and maybe the picture and all of the related details of this story. I want to go grab that in one shot and render it really quickly to the page. I might use a document data store to avoid those joins. I'll just do a get by ID based on the URL and render that really quickly to the page. So a document database can be really cool. Next, let's look at a graph database. Now, graph database is really interesting in that it doesn't just have data, but it has relationships between data. Now, this is quite a bit more than just foreign keys. Graph databases, they have nodes and they have relationships that may be directional. So I can think of this as friends and friends of friends. What makes graph databases really powerful is that graph databases allow you to query into those relationships with very well-known syntax. So here's that thing. Let's go dig into that relationship. Here's that arrow between the relationship. And we can store data not only in the nodes, but also in the relationships. That's really cool. It's SQL-esque, but it's not SQL. So how is this different from a SQL table with 2 foreign keys? It's about that query syntax. The query syntax allowing us to do the friends and friends of friends without, rejoining the table 2 and 3 and 4 times. That's what makes graph databases so powerful. They are optimized for these networks of relationships. So on the upside, I get really fast joins across these relationships. I can store data associated with these relationships. It's great for that type of thing. On the downside, because we've focused on the speed of the relationships, we sacrifice other features associated with SQL databases. Cross-table joins in graph databases are not usually a thing, or they're really expensive to do because we're focusing on the relationships between things, not on joining things. So here's some examples of graph databases. Graph databases are great for messaging apps, for social networks, perhaps for a recommendation engine when we want to understand how is this product similar to other products. These might be great uses for graph databases. And when you're in a micro database environment, you can have a graph database for that network detail and then a different database for the other things where we need joins. Next up, key value databases. Given a key, read or write a value whose value is anything. Maybe it's a JSON blob, maybe it's binary data, but we can use whatever we need to be able to store that data and then deserialize it back into place in our application. Now with a key value database, that binary blob is, well, kind of opaque to the engine. It's just a big thing. If we squint real hard, and this analogy definitely falls down pretty quickly, we could think of this as a table with a primary key and a big binary blob column, those two columns. Now it's great when I want to read by ID, and the data in the blob doesn't need to be the same between every record, but I can't really read the data by the value. I can only really read the data by ID. So on the upside, it is really, really fast for those by ID columns. I can store different type of data in each row, and it's more or less schemaless. Once I get the data in that row, I can deserialize it with whatever mechanism makes sense. Is this HTML? Is this JSON? Is this binary data? Ultimately, it doesn't matter. The thing that is reading that key knows how to deserialize that value. On the downside, I really can't query by anything else other than the ID. If I do need to query by something else, for the most part, I'm looping through all of the IDs, reading each one, deserializing it, and then filtering it with a different engine. So if I do need to read by other kinds of data, then a key value store probably isn't a great choice. But where key values really, really make sense is caching or configuration. Here's some examples of key value databases. In that caching mechanism, I'm reading by ID. Maybe that ID is the URL or the configuration name. And that value then is specific to that particular thing. If I don't have a value, let me go get the value out of that more expensive data store and store it here in this cache. Key value databases. Next up, Timeseries databases. Ooh, a great question. What is a CMS in the context of a NoSQL example? Mongoose is a great CMS associated with NoSQL. Actually, no, that's over Postgres. What is a CMS? Oh, a content management system, not an ORM. A content management system over a NoSQL database. So I might have a content management system like WordPress that allows me to create the post and all of the particulars about that post and save that in a NoSQL database. That would be a CMS over the top of a NoSQL database. Great question. Thanks. So Timeseries databases. Timeseries databases are focused on fast ingest of real-time events, and I can query based on a time window. What's really cool here is typically when I query, I end up with a cell that has exactly one value. Now in this case, my columns aren't a single value, but my columns are a time window. Show me all the events within this 5-minute window, or within this hour window or day window. Now that I have a window of events, the cell in this spreadsheet metaphor has many values. And so now I can do really interesting things like give me the max or min or sum or average of all of the data in this cell. Because I have that window, because I have that bucket of data, I can do some really interesting analytics. Give me the first one or the last one or the average or any unusual ones. On the upside, Timeseries is really great for those time bucketed type of experiences. On the downside, I've traded that feature for other features. So it isn't a great general purpose database, but it is a great Timeseries database. Here's some examples of Timeseries databases. It's fun when I have data that is very time sensitive. So perhaps I have events from IoT sensors or from mobile devices, and I need to be able to identify maintenance windows or unusual circumstances that could perhaps require maintenance. I can do that with a Timeseries database. I can find the events in this bucket, and I can find missing buckets. Timeseries databases are great when I have timed events. Next up, text search databases. Text search databases focus on querying. That might be paired with a natural language processing engine, so we get kind of a search engine experience. But for the most part, text search engines have this inverted index, kind of like the index in the back of a book, whose sole purpose is to find the documents that contain this query term, or find where in this document it has this query term. The natural language processing engine may help us refine intent and may get us to alternate words that may match our search term. So with this text search database, it's really optimized for that case. Which documents have this match, or where in this document is this match? So it's focused on that text search. It has no concept of relations between documents. There's no joins. I just have that inverted index. And let's talk about stop words. So there are stop words like a and un and the, of, that may not have any semantic meaning to our context. So we may choose not to index these words. These stop words aren't relevant to us. That could get us into trouble though. Well, what if we're working in a different language? Maybe that character really does have meaning in different languages, in different contexts, in different domains. Additionally, if we've dropped a and av and road and those things that don't have a whole lot of context, what about that street that's called Avenue A? If we drop av and we drop a, is this street now null? Stop words are very specific to our domain and our culture and our language, and so we can get in trouble with stop words when we implement them in a text search database. So a text search database, here's some examples of text search, and they're great for finding content within documents. Now, because we can't do joins or relations, any other metadata about this document, we probably want to store in a different place so that we can say, well, let's filter down our list of documents to only the documents that are in this date range or in this topic, and then let's search them in our text search database. Similarly, object stores. Object stores are great for storing big binary blobs, maybe database backups. It's kind of like a key value database if the value was really big. We can think of these kind of like a file system. And in many cases, our object store is a file system. But we might also want to look at blob stores like Amazon S3 as this kind of metaphor as well. In that case, the key is a path, but it's a simulated path. And we're just using slashes as our own little decoration of organization. It's not really different folders within a file system. Or maybe it is, Amazon's not going to tell us. So with these object stores, they're great for very big things. Video files, audio files, database backups. They're great for that get by ID scenario. But if I want to say, well, when is the latest version of this file in all the backups? For the most part, I'm going to have to take each backup, deserialize it with whatever way makes sense, and then look through that with a different search engine. So object stores are great for that get by ID case, but they're not great for other cases. When I have that additional metadata, maybe the files that are stored in this backup, or the time codes associated with this video, or the creation date and time, I'll want to store those in a different database where I can do more random queries against this data store. Once I identify the object blobs that I need, I'll do a get by ID, I'll deserialize that blob, and I'll take a look at its content. So object blob stores, here's some examples. They are great for storing big things that need get by ID type access, not random access. Next up, column stores. Now column stores are really, really interesting in that column stores kind of take that relational model and turn it on its head. On the left, we have a standard relational database. On the right, we have column stores. On the left, maybe we're storing state or country. Now there's only so many countries in the world. There's only so many states or towns in this country. And so if we store a country column, then we can compress that data a lot more. We can store a lot of data a lot smaller. That's perfect. And then in this column, we can link off to the rest of the row, the rest of the fields in this row, which don't necessarily all need to be the same. Column stores are great for analytical data where I need to be able to bulk read a whole lot of things. Show me all of the things in this state. So on the upside, we have much better compression for large data sets and faster seeks. On the downside, we get slower random reads and writes. So column stores are great for analytical tasks, where they're not great for transactional tasks. Column stores, here's some examples of some column stores, and they're best used for analytical workloads, OLAP workloads. Next up, Nosql databases. Now this may be one you've not heard of before. We can think of this as SQL but partitioned, or SQL with an SLA, where we know the performance characteristics of our database and it doesn't scale with the size of data. We can add more horizontal hardware to allow us to speed up our database. So in this case, we're using MemSQL as an example. We have aggregators that accept client queries, and that aggregator will then proxy that query off to leaf nodes that have our data stored in partitions. The leaf nodes will collect the data that is responsible for answering this query and feed that back to the aggregators where the data can get combined back into a deterministic result. Now in this case, we have a whole lot of benefits where we have easy mechanisms for compensating for hardware failure. We can more easily scale up our system just by adding commodity hardware. Nosql databases are really cool in being able to create that benefit of the scaling of a NoSQL database without the trade-offs like losing ACID compliance. They are SQL databases, but scaled horizontally. NoSQL databases, they're great because they're cheaper to scale. On the downside, when I do a join, there may be some network activity to be able to move the rows onto the leaves that need to do that join. Now, all of the leaves should be in close proximity, so this network traffic is definitely over the LAN, not over the internet. So it's definitely low latency, but there is some latency involved in network traffic. So NoSQL databases, here's some examples, are great when you're outgrowing your database. If your dashboard has that spinning wheel or your application has that wait timeout because it's not really performing, that's the time when a NoSQL database may make sense. You could also look at the strength of your queries as well. But NoSQL databases are great when you have very big data sets that you need to be able to scale horizontally, but you still want them in SQL so you can do joins and queries. Now, bonus round, hybrid databases. Hybrid databases include this type of database plus something. Maybe it's a SQL database, but it also has a JSON column, so it's able to do NoSQL-like things. Or maybe it has time series windowing functions, but it's also SQL. A lot of our databases move in this realm so that they can get to be close enough to the other things. A lot of databases are becoming hybrid databases, which is really cool. Here's the money shot. Grab your camera. Here's all of the databases that we looked at today. Kind of a brief overview of what they do and what they're best for. Here's another one where we took a look at the architectures. We started moving from monolithic to micro, and we had the microservices, but we talked about mechanisms for getting to micro databases as well. If you are stuck with a monolithic database, use bounded context to start simulating a micro database so that when you're ready to move to micro databases, you can do it. Micro databases are great when you have the automation to spin up databases and enroll them in authentication and backup strategies automatically. Remember, when you get to micro databases, they don't all need to be the same kind. We looked at lots of different kinds of databases and when each one makes sense. My recommendations, in production, use database as a service, because database as a service, they'll take care of the point-in-time restores, they'll take care of ensuring authentication and backup. It's really great in being able to lose that worry, outsource that worry. If you have more than one database server, use automation to be able to get it in place. Choose SQL by default because of that ACID compliance. If you have a need that is very specific and another database type exactly matches it, then that's when you can find another database that exactly matches that type. A hybrid database may be able to help you in getting to that goal as well. This has been a lot of fun talking to you about micro databases. You can reach me at rob_rich on Twitter, and you can grab these slides right now at robrich.org. What are your questions? What is a CMS in the context of a NoSQL example? I'm not sure we did a great job with this. Kyle, ask again if we didn't. CMS, that content management system, is great for producing those articles, those product catalog listings. And at that point, that's where you do want a really fast read by ID. And so a CMS over the top of a NoSQL database allows you to store all the details associated with this post or this product, including their images and their author and the related details, all in one spot. So that then as you go to render that page, it renders really fast. One of the questions I often get asked is, so which one should I use? Well, I very specifically tried to avoid pointing you to a particular database vendor or a particular database type. SQL is a good default if you have no other options, and I bet your monolithic database is SQL. But I would invite you to explore in smaller projects or in less critical applications using other database types that best meet the needs of that particular application. And if SQL is that perfect data store for that microservice, then by all means, it's a great choice. If you run out of capacity in your SQL database, reach for a new SQL database that is partitioned and distributed so that you can reach the SLAs that you need. Here's a great question. When using SQL as a microservice, would the, I clicked on it and lost it. Would the optimum setup be to separate databases or separate server instances? Great question. So how best do we implement this? Probably in the shortest term, we're going to reach for a database as a service product because those will keep track of all of our details for us. And that's really cool. If the data store is going to be really small, then we might be able to map a volume into our container and store that database together with our service. But probably we're going to have a different container with our data store in it, or a cluster of machines. Maybe we'll have a stateful set that includes all of the nodes for our database. Probably co-locating our data store and our microservice into the same container would be problematic, but co-locating them in the same region or the same redundancy zone is good for increasing performance. I would invite you to explore how close or how far you need to keep the data safe, but also keep it fresh and relevant. And together with your organization, find the best practices that work great for you.
All right, wonderful. Thank you very much for all that information, Rob. It was a pleasure, and we appreciate having you at our conferences here. We hope to see you again in the future.
Most definitely. This was so much fun presenting. If you find a question tomorrow or next week, or you're watching this video online, grab me at rob_rich on Twitter, and let's continue the conversation.